So Professor Xinzheng Lu is a professor and the head of the Institute of Disaster Prevention and Mitigation of Tsinghua University. His major research interests cover earthquake engineering and collapse prevention of structures. He has published more than 200 papers in refereed journals. Professor Lu has been recognized as the most cited Chinese scholar in the civil and structural fields by Elsevier from 2014 to 2019. And I can attest to his prolific papers and the number of papers that come to the Journal of Structural Engineering and many other journals. We are very fortunate to have you here, Professor Lu. I understand the sacrifice that you're making by staying up so late, and we really appreciate it. Thank you very much. So the floor is yours.
Thank you, Sherif. Thank you for inviting me and giving me this opportunity to present some of our research together with my team. And also, thank you very much for the formal presentation, give us a very clear idea that what we need for resilience. And today I will present some of work we have done in our team, particularly on how to do the disaster simulation, because we know that this is very important. So here is the outline of my presentation. So first I will talking about the research background. Okay, so we all know that the resilience is very important for a city. And when we study the resilience of city, mostly we need simulation models. Most of the models we are using are empirical models, like the damage probability models for the earthquake disaster. However, that these models have some limitations. For example, that in many countries like China, we don't have sufficient earthquake in recent years. So that we don't have a good empirical model for the modern cities. And also that the civil engineering is developing very quickly. Here shows the two figures of Shanghai, and we can see that, you can see that after 20 years, the city of Shanghai have changed quite a lot, and a lot of new structures are emerging, and we don't have a good empirical model for these new structures. Okay, so that addressing these two challenges of the existing empirical models, we think that maybe we can move forward to the physics-driven model or physics-based models. We think that the advantage of this model is that it's more reliable, efficient, adaptive. And today I will talking about three disasters and their corresponding physics-driven model, including for the earthquake, we use the nonlinear time analysis at a city scale. And for fire, we can use the thermal pump and radiation-based fire suppression model. And also for the wind, we can do the large area simulation to simulate the wind flow in the community scale. Okay, so first we are talking about the physics-driven regional earthquake simulation. Yeah, that is the idea of our model. So we combine the structural dynamics models and the city scale nonlinear time history together. So we get a ground motion, we build the structure model of each building in the city, and we do the time history analysis. Then we can know the response of the entire city subject to earthquake. So the advantage of this model is that it strictly follows the fundamentals of structural dynamics. It can accurately represent the features of different buildings and also different ground motions. So we proposed the two levels of two different levels of fidelity of models for buildings. For conventional buildings like the multi-story building or tall buildings, we can use the multi-degree of freedom shear model or MDF flex shear model. And for some very special buildings, we can use the refined finite model to build a high fidelity models. And we need to know the interstory behavior of these MDF models. So we can combine these empirical formulas for the vibrant period. We can know the design strength from the code, and we can know the all strength factors and the deformation or ductility of these different structures from the sufficient test data. And also the advantage of these models, a structure model, is that we can use different kind of resolution of data. We can use GIS data, we can have the build information or structuring. We can step by step improve the accuracy of our different model. Okay, so here is the comparison of, oh, sorry, it jumps. So here is the comparison of the accuracy of this model. We can compare the result with the test data. One can see that the prediction model agree well with the test result. And also we can compare it with the monitoring data, and also we can see that it agrees with the real earthquake monitoring data. And also we can combine it with the real earthquake damage to the buildings. This is the earthquake in China. We can get ground motion during the site. We can get the damage for each building. And we can see that with this city scale time history analysis, our prediction is much better than the damage probability matrix model. So that this shows the advantage of the proposed model. And one of the very important advantage of this physics-based model is that it can provide a much better visualization of the disaster consequence. Because when we're talking about resilience, we need to talk about different stakeholders, and many of them are not professional people. So that if we only come to the data number, it's not easy to understand. But when we show there the animations, they are quite easy to understand what happens when their community is subject to a disaster. It's not only for earthquake, and also for wind, fire. I will talk about this later. Okay. So here is one of the example. So this is 230,000 building in Tangshan city. We did the simulation because the city is destroyed in an earthquake about 40 years ago, and we can do simulation of the entire city. We can know the shaking of each building, and we can know, okay, this is the red part of the buildings. Some of the old buildings not good enough that it will collapse in this earthquake. But the most important thing here, I'm sorry that the animation is not so fluent, but you can still see some of the outcomes that there is about 100 million square meters of building that come to the yellow, means that the building is so severely damaged that it cannot be repaired after the earthquake. So that clearly shows the demand of resilience, and this result is quite easy for the city managers to understand what will happen to their city after the earthquake. Oops. Okay, so here is another example that we simulated the entire Beijing CBD area subject to a magnitude of 8 earthquake about 300 years ago happened in Beijing. And we can see that many of the tall buildings, they go to the yellow color, means that the damage of the building come to the moderate damage. And such kind of moderate damage to these tall buildings are very hard to repair. So this also clearly shows the requirement of resilience for this city area. And we also combine this three-dimensional visualization model with the UAV three-dimensional photos, so that we can clearly show the very realistic shaking of each building subject to this earthquake. And that will be helpful for the non-professional people to understand what will happen to their city and improve the demand for the disaster prevention capacity. And we can know that from after some of our work with cases, we found that the city scale time history analysis are both very functional before earthquake and also very useful after earthquake. For example, for the urban planning, disaster preparation, or emergency response. For example, we can use it for the seismic loss assessment. We all know that some good document like FEMA P58 already provide very good loss and resilience evaluation method. And the city scale time history analysis provide all the engineering demand parameters that we need for such a kind of evaluation. So we can use this method to know the detailed damage. For example, for the Tsinghua campus, we can know the detailed damage of each building and each component. And we can also know that the damage of the entire campus and what we need due to the impermeable deformation and that we need for the resilience. Another example we did it, the similar work but much bigger is for the entire Beijing city. We get the 68,000 resident buildings from the internet of the Beijing city. We simulate a magnitude of 8 earthquake. we simulate the repair procedures and the repair labor demand. And then we can know that after the earthquake, how the recovery procedure and how we optimize the distribution of the workers to make the repair procedure of this city more efficiently. And we can also use it for some secondary hazards. For example, the falling debris that may kill people surrounding the buildings. And we do the temperature analysis. We know when the component will be damaged. We know the velocity of the floor, so we can know the falling distance of this debris. And then we can do the evacuation experiment to know the people moving speed subject to this distribution of debris. So with this all technology combined together, we can use it for the urban planning, for example, that we can use it to know that the distribution of falling debris and select a better location for the evacuation shelter. And we can also use it for the emergency evacuation simulation and know the risk and the more evacuation time due to the distribution of the falling debris. And such technology can also be used for the urban planning of the cities. This technology has already been quite used in cities, in many cities in China, like Beijing. And this technology also can be used right after earthquake, provide the post-earthquake assessment. The traditional way, we know the earthquake magnitude, then we predict the intensity and we predict the loss. All these procedures have significant uncertainty. And with this technology, we can use the ground motion from the strong motion station and input the entire ground motion to do the nonlinear time histories. And with this procedure, we have much smaller uncertainty. So we have a system called REACT, real-time earthquake damage assessment using city-scale time history analysis. So every time after earthquake, we get a ground motion, we put it into the building inventory, and we know the detailed damage of the building in that area, and we also know that the distribution of the damage. So here is an example that in 2017, there is a magnitude of 7 earthquake in China. And after the earthquake, some agency use the traditional way to predict the damage and say, okay, there will be tens of thousands building will collapse. But with our method, we predict hours after earthquake that there is a very small possibility of collapse. And after 1 month, there is the site investigation said that there are about 73,000 building damage, but only 76 collapse. So the collapse probability agree quite well with our assessment. So this method is already being used in Chinese Earthquake Network Center, and it's played some critical role in the recent Chinese earthquakes. And we also try to use this method to simulate some of the damage in United States, like the 2018 Anchorage earthquake and the 2019 California earthquake. And this is the predicted seismic damage right after earthquake, not after the earthquake. And I think the results are quite interesting. And also this work has been done, we work together with the SimCenter so that many of these damage simulation and loss simulation can be found from the source code of SimCenter. I think Professor Dialing will give a detailed introduction of this work. So I will go through it quickly. So this is some big area. This is the simulated ground motion. And okay, so after input the ground motion to different buildings, we can know the shaking of the entire San Francisco downtown, and we can know the seismic loss and also the repair time. And after the earthquake, we're talking further about the fire and the wind simulation. So first we go to fire. We all know that fire is also a very important hazard to community. and we need to simulate it. The traditional way, oh, the speed is, the speed of the slide is horrible. The traditional way use empirical models, and it's have many limitations. And now people are moving forward to the physics-driven models. And it can, so we have this physics-driven fire simulation models. We have the physics-driven fire simulation together with the physical-driven visualization of the fire scenario. And also we can combine it with the earthquake simulation. So we can have the physical-driven earthquake simulation and then come to the physics-driven of fire following earthquake simulation. So this is some validation. We can see that the proposed model agree very well with the real fire cases. And here is the case study. We select a Taiyuan city in China, simulated a fire following earthquake. So here is the result. You can see that the arrow point here is the location of the ignition buildings. We have a west wind of 3 meters per second. You can clearly see the fire spread along with the wind direction. And we can see that the total burning area will increase after the building damage, and the wind speed will have some significant effect on the fire burning area. This shows the advantage of this method. And we also can use the physics-driven model to simulate the fire induced smoke after earthquake. This scenario is the simulated scenario. We can see that it can provide a very realistic simulation of this fire following earthquake. And also that we now know that the wind induced not only the shaking of the building, but also the damage of the no-struct component will also result a big impact on the community. The empirical model cannot consider the very completed building building configurations, and the wind tunnel test is quite expensive and complicated. So we can use the city scale time answer together with the city scale large edge simulation. So we can use the CFD to simulate the wind pressure on the building and use the time history analysis to know the shaking of the building subject to such wind. So this is the flow chart. We have this wind pressure on the building. We're mapping the wind pressure to the wind load on the building, and we do the time history analysis, and then we do the visualization. So we can know that the dynamic response of the building subject to. So here we still use the San Francisco as an example. We select about 500 buildings in San Francisco downtown. Here is the computation, CFD computational domain. So this is a very big model, and we have a 700 return period of wind, and we use the large edge simulation to this situation. And here is the time step and all these boundary condition. And this is the result. We can see that the simulation results agree quite well with the window tunnel test. So this shows the accuracy of this model. And here shows the wind flow through these tall buildings. We can see that with the large edge simulation, we can know the dynamic change of the wind in this situation. And we can know that wind pressure on the building is quite different with the design code because the complicated building configurations. I need to go through it quickly. And here we can clearly show that the shaking of the building is subject to this dynamic wind load. And finally, we can evaluate the occupancy comfort subject to this building shaking. Finally, I was talking a little bit about the database for this simulation. we call it a multi-hazard simulation framework based on city information model. All these physical dream simulation, we need quite a lot of data, and common data cannot satisfy this requirement. So you can see that we can combine the building information model and the GIS model together to build up a city information model, so they can provide a different level of details data for our simulation. So we built out the entire framework from the data transformation to the physical driven analysis and then to the high fidelity visualization. To demonstrate this framework, we use the Tsinghua campus example. We have the entire campus and one very detailed building information model for some important buildings. So here the earthquake simulation, we can clearly see that the damage to the entire campus and where the critical locations, critical buildings. And we can do the fire simulation to know the fire spread and the fire scenario of this area. We can see that the burning of the fire and the change together with the time. And also we can do the wind simulation, and we can know the dynamic wind load on different buildings, and we can evaluate the safety of those structural components subject to this wind. This is 3D simulation for the regional scale, and we also can do it for the single building scale. We can use the city information model, and then we can give the detailed building information model to the finite model to predict the seismic damage for this particular building. And we can also translate from building information model to the FDS model to evaluate the fire damage to this building. And we can also transform the building information model to the CFD model to predict the wind pressure on this building. So with all this technology, we can say that this come to our conclusion, so that with the physical-driven simulation, for example, we take San Francisco as example, we can do the earthquake simulation, fire simulation, and the wind simulation. And all this simulation is more adaptive and reliable, and also that the visualization is very realistic for the professional people to understand that. And in the future, all this model can be based on the city information model to provide the uniform data format for the simulation. So this is the acknowledgement for all the people who give us help and all the agencies give us support. And that's all for my presentation. Sorry that due to the internet, there is some delay, so it'll take a little bit more time. Okay, thank you.
Thank you very much, Professor Liu. This is a great presentation. I appreciate all the animations. I love animations, and yours really are out there. So very, very nice. Regarding the internet, we're connected all over the world. So these are things that are inevitable. So again, for speakers, just click once and wait, and hopefully things will get through. But I think you did a great job, and it looks like we have many questions. So we have 13 questions right now. I'm gonna see what we can cover in the time we have. And if there are any unanswered questions, we will collect them for consideration for discussion during the panel. So the first question is from Elena Lund. Thank you for your interesting talk. How does the computational effort of your method scale with the buildings being modeled? Could you also give some insight about how sufficient information on the buildings are collected to provide relatively accurate nonlinear behavior?
Okay, so that for the building simulation, we have a fundamental requirement. We need at least 6 parameters, like the height of the building, the structure type, the construction period, the functionality, the number of stories. So with these fundamental parameters, we can predict the nonlinear behavior. We have a mapping rule from this general information to the structure model. Of course, you have more data, we can further improve the nonlinear model to give a more accurate prediction.
But where do you get the basic information about the structures? Is it just the square footage, the type of construction? Is that what you use? The number of floors?
Yeah, for most of the building, we just need the height, the structure type, the construction period, something like that.
Okay.
Yeah, and then we can map it to the strength and deformation parameters.
Okay. Thank you. The next question is from Professor Jamie Padgett. She says, thanks for the valuable illustrations of regional scale physics-based simulation of earthquake impacts on a large building portfolio. How did you arrive at unique finite element models of 200,000 plus buildings using the nonlinear time history analysis? What types of data and model assumptions are required? It's very similar to the first question.
Yeah, very similar. We have the papers. I listed the name of the papers on the bottom of the slider, so we can go to the details of these questions. Yeah.
Thank you. So from David Bonowitz, when you simulate a city of 50,000 plus buildings, who is your client, and what do you think their expectations are in terms of reliability of these models that graphically show very specific performance of individual structures? What will their attitude be when, not if, the actual damage is different, like numbers of hundreds of casualties or thousands of collapses are more defensible?
Yeah, actually, that's also a very interesting question. Actually, that in many situations, the city manager want to know the performance of their city after the earthquake. So when we have the technology, the city management, they are very happy. Administration, they are very happy to ask us to provide this simulation to improve their preparation of their cities to this disaster. And for the next question, I think you are talking about the emergency response after the earthquake. So of course that after the earthquake, many agencies will provide their estimation, their assessment of the consequence of this earthquake. In some cases they are accurate, some cases they are not accurate, and we also provide our evaluation. And we are lucky that currently our evaluation is performs quite well. So we have more and more predict from the agency that they more rely on our prediction. Yeah.
Okay, thank you. So the next question is from Mariam Akram. She says, Professor Liu, what software do you use for fire simulation and plume dispersion? Do you solve for the flow field, or you just consider wind magnitude and direction?
Yeah, this is a good question. Actually, that we do the fire simulation with a simplified plume model and the radiation model. So we don't go to the CFD simulation. We just use this simplified model that, and the details of the model also listed in the paper. Yeah.
Thank you. Jian Ma says, thank you for your presentation. Very amazing, and indeed, very amazing. I have a question about how to get detailed information to develop fragility models for older buildings. Example, brick masonry buildings.
Yeah, the brick masonry building is a very local dependent, that the masonry building in China or in Italy may be quite different. We connect more than 100 masonry buildings in China, and there we can know the deformation and the strength parameter of this masonry building in China. So that is what we did for this work.
Okay. So Ahmed Abdelhadi says, thank you for the interesting talk. I have a question related to the falling debris from buildings in earthquakes. Is this phenomenon modeled using physics-based models? If yes, what is the basis for this model?
Oh yeah, this is the physics-based model. So you can see that this is something like a free body falling with the initial velocity. So you have a damage of this brick, and the brick have an initial velocity, so it's falling to a certain distance according to their initial velocity. Of course, when it hit on the ground, it will jump some distance, but they also have the model to simulate that behavior.
Okay. So this is from an anonymous person. Do you consider other infrastructure except buildings? If yes, can this also include interdependencies?
Yeah, this is a very good question. Currently, we are major working on buildings. My colleague is working to extend this technology for some lifeline networks, but I think there's still much work to be done to build up the physics-driven model for these other infrastructures. In our group, we have not solved this problem.
Okay. This is amazing. We have 19 questions. I've asked you quite a few of them. I think maybe we have time for one last one before we switch to the next speaker. So I'm going to choose one kind of a trend of here. So from Wilfred Jima, what is the difference between the RED Act, RED, ACT, and CAPRA GIS in a large-scale seismic assessment of buildings?
I'm not quite clear about the Capra GIS software. So I cannot give you a detailed comparison. I just said, okay, our model is based on the city scale simulation. So this is a very special technology. Yeah, that is.
Okay, thank you very much, Professor Liu. Your talk has generated a lot of intense interest. Again, the questions will be collected and they will be considered for discussion later on. Thank you very much. We really appreciate you joining so late at night. Thank you.